This particular system, Cancri, is actually a binary system that has the shortest orbital period ever observed yet, of 5 minutes. There are two white dwarfs. They are only 50,000 miles apart, only 1/5 of the distance between the Earth and the Moon. They are orbiting each other every 5 minutes at 1,000,000 miles an hour. This is a Chandra observation. Over time, it has determined that the orbit is decaying by 1.2 milliseconds per year, which translates into them moving closer together 2 feet per year. So eventually they are going to come together and form what? A more massive white dwarf, a neutron star, a type 1a supernova event, or a weak supernova event that only damages but does not destroy the white dwarf. I think I read somewhere that these two will probably coalesce into a larger white dwarf because I think they're both fairly small in mass, less than 1 solar mass each. So we have these white dwarfs. We have them in a binary system with a companion star, white dwarf, another white dwarf, a red giant, any main sequence star whatsoever of any mass. As long as they get close enough for contact to be made, then you can have a situation that can lead to a type 1a supernova event. Stars have what is referred to as a Roche lobe surrounding them. Within the Roche lobe, within that defined space, all of the material within that space is gravitationally appended to the star, the center of the star, or the center of the stellar core. It's all gravitationally bound to the object. But the Roche lobe is like tear-shaped, and it's tear-shaped pointing towards the binary star companion. So you can see that these two Roche lobes actually make contact, and they're making contact at the Lagrangian point 1. And when that happens, they're close enough, contact right there in that one spot enables the stronger gravitational field of the white dwarf to accrete some of the material from the surface of its companion star. So that allows mass transfer through that point, and then it forms a hot spot and then an accretion disk around the white dwarf and sets up the scenario of instability, which can lead to further destruction. There are also types of white dwarfs. They're a little bit more complicated, actually a lot more complicated than you would think. But basically, there are classes of white dwarfs. They have classification systems for them. And you can have usually they are classified by the letter D, followed by letters and numbers. Some of them have 4 and 5 letters and numbers after them. And the other letters are all mostly because of their spectra, because they do have different spectra. Okay, and the cores themselves are different also. Basically, you have a core. If you had a progenitor star that evolved into the white dwarf that had a low mass, then you're going to have a core that's predominantly helium. If you have a sun-sized star with about 0.8 to 8 solar masses that ends up in the white dwarf, then you have usually a carbon-oxygen core. A more massive star, you can have an oxygen-neon magnesium core. So the cores, it isn't always carbon, carbon, carbon. It depends upon exactly where that fusion process ended when the white dwarf formed, so they do have different compositions. They also have a very thin atmosphere of normal material on the surface that then radiates away over time, but and again, it produces the spectra, just like stellar spectra. The atmosphere of stars absorbs everything being emitted from within the interior of the star and then readmits it away. Well, white dwarfs, stellar atmospheres do the same thing, it only takes a very small difference to produce a larger effect in the spectra, because these the atmospheres are right above the surface of degenerate material, where you have kinetic energy of these electrons doing relativistic speeds. So it puts a lot of pressure on that atmosphere, and you will see the results of that when I show you a couple of the spectra. So there are atmospheres that produce spectral lines where you have only helium or only hydrogen or neither one or the other, but lots of metal lines. There are ones that have lots of metals and no helium, no hydrogen. And secondary features include how magnetic they are. White dwarfs can be rotating, have magnetic fields, emission lines, all kinds of weird, and some of them are variable. So there's a lot of different types and classifications of white dwarfs. One of the type 1a supernova remnants is SNR 0509-67.5. This here is the image you're looking at is a combined composite observation from Hubble and Chandra. Chandra is the blue energy in the middle from X-ray, and then again here is the Hubble, what Hubble sees, and this is a composite of the two together. This type 1a supernova remnant is actually located in the Large Magellanic Cloud Galaxy. It is 160,000 light years away, and it happened about 400 years ago, so it's still fairly young and expanding at a rate in an excess of 11 million miles an hour. SN 2011 SE is even further away. This event took place in the Pinwheel Galaxy, which is in the direction of Ursa Major, which is 20.87, that's what they say, 20.87 million light years away. So this one was actually quite a catch. It was observed by the Palomar Transit Observatory, which is always looking for newly forming supernovas, and they actually saw it 2 weeks before it met its maximum peak output of brightness, and they followed it from 2 weeks before maximum brightness all the way through more than 3 months afterwards. So it was a really long observation through the entire process for this particular supernova event. And it behaves just like a textbook, an absolute textbook type 1a supernova event, and it was thought that the white dwarf had a carbon oxygen core, and it had a main sequence companion star. SNR G 1.9 plus 0.3 is the youngest type 1a event in the Milky Way galaxy. The blue data here is radio data from the Very Large Array in Socorro, New Mexico, and the orange is Chandra X-ray data. The Chandra data was taken in 2007. The radio data was taken in 1985. So the difference in those two sets of observational data is 22 years, and that was used to interpolate backwards in time and tells us that this event took place only 110 years ago. So it is definitely the youngest one. They try really hard to determine what was the trigger mechanism for type 1a events, because type 1a supernovas are used as standard candles to determine the distances in galaxies far, far away, and also as a way to measure the rate of expansion of the universe. So if you want to get that expansion rate correct, you need to know exactly what the trigger mechanism was, because the brightness that you use to calculate that is different for two white dwarfs becoming a type 1a supernova, or one white dwarf with material from an accretion disk causing that type 1a event. So here we go, Tycho supernova event. Everybody should be familiar with Tycho. We use him over and over again, There's a reason for that. It happened very recently, 1572, and it has been observed several times, all kinds, and every time it's observed and research is done, you learn more and more. So this is becoming a really well understood event, which will help us to understand other similar Type 1a supernova events. It was a mystery for a while with the Tycho supernova event, the little tiny little curved, bright little arc that was within the remnant. It wasn't quite sure what that was. And later, more observations and more analysis of the data showed that that is actually material stripped away from the atmosphere surrounding the companion star when this event took place. So Tycho is the result of a thermonuclear explosion due to accretion of mass that exceeded Chandrasekhar's limit because of a binary companion star that it was accreting the material from. So using that, they were able to calculate the orbital mechanics for this event and determine the location. That gave them the location of the companion star from the direction that Tycho is moving in at the rate of motion for it. That allowed them to calculate where that companion star, where they could look for it, where it might possibly be, because they would know the direction and the velocity. And there is still, I think, some dissenting opinions, but I think that some, or if not most, and some scientists do believe that they have found the companion star for Tycho. It's called Tycho G,